Hello, this is to supplement some of our classroom discussion on arrays and addresses in C++. We will go over the size of operator, the idea of indices and how they're computed, dereferencing and pointer syntax, the use of this star. We'll talk about the address of operator here, and we'll conclude with passing an array to a function. All right, here I'm creating an array at the top. Notice I do not fill in the size. I'm going to just type in some numbers, and a giant block of memory will be allocated. The compiler at compile time will fill the array up. At compile time, since it's filled the array, it knows the total amount of bytes that it's used, and it knows the size of an integer. So based on this information, we can compute n. What is n? The number of integers I actually have in the array. So I don't have to keep count. You say, oh, 3 is an easy number, but what if I had 50 numbers in here and I lost count? First thing we'll do is we'll run the code and we'll ask it, what is the size of an array? This is test code. We'll ask it for the size of an integer. Then what I'm going to do is I'm going to ask it to print out the starting address. Recall, the starting address is just the name of an array. So I don't know where this array lives. And I'm going to say move over 0 positions from it. So that won't change anything. 0 plus a number is 0, the number. However, I'm also going to do something else. I'm going to say wherever it starts, go all the way up n. But it doesn't mean add the number n. This actually means to the compiler, it'll move over n integers in length. We'll take a look at this more closely. When the code runs, it says, the computer says, I've allocated 12 bytes of memory for A. So this thing here is 12 bytes of RAM. I don't know where it lives, but somewhere it has 12 bytes of RAM. We also know that it's filled with integers. So if I take a total of 12, divide it by 4, you'll find out we have 3 integers. The start of it is, this is a hexadecimal number, 009 Charlie Fox, Bravo 50, etc. And we notice the numbers are all the same digit, same digit, same digit, same digit, except here. There's a difference. What is that difference? It's a hexadecimal number, so I have to look up the letter C, and the letter C is a number. It's the number 12 in base 10, which if we go back, here we see the number 12. It's 12 bytes from the start of the array to the end of the array in memory. 12 bytes. Next, another way to reference this array is I could say, go to the address A, move over 0, and tell me what's there. Go to the address A, move over one integer, not the number 1 as in 1 byte, but 1 integer. The compiler will do this automatically. It will actually convert this to 1 times the size of an integer. The compiler, you don't see it, but it's hidden in there, the size of an integer. The compiler does that dirty work for us. So here it says, go to memory address A, move over 2 integers, show me what's there. And that's why when you look up here for the output, you see the numbers 1, 2, and 3. Again, I really don't know where A lives anymore. And it doesn't matter, as long as I know the variable A where it's supposed to be. So here's more detail what's going on. The minute you create these angled brackets, right, like this, the compiler says, oh, angled brackets for A, it will take the name of the, well, I'll start here, the name of your array A in this case, and find out its address and plop the address in there. The compiler goes up here and says, oh, you're full of integers. I will compute the size of an integer. And every time you put a number here, the index, it will just turn around and say this number times the size of the data in the array plus the starting address equals the item. So in this case, we're looking at item 0, which is 1. But I say I don't want to see the item 0. I want to know where it lives. Where does this number 1 live? Then I'm going to ask, calculate the address of A1. A1, after I calculate its address, don't go to where it lives, because normally this says go inside the darn thing. Don't go inside. Just show me where this thing lives. That's what the address of operator here is. Show me where the thing lives. And the interesting note to remember is it's these braces here. The minute you write these braces in, the compiler does all this work for you inside here. It's all done by the compiler. And that's what we want. Here's the actual run of the code. Notice this is the last item, number 2. Index number 2 is the last item in our array. And notice its address here based on the first and second. They're going to be 4 bytes, 4 bytes, 4 bytes in length. Multiple runs, well, before I get to multiple runs, I was using the Visual Studio and I asked it to compile different ways the 64-bit machine in the old 32-bit machines, the x86 architecture. The x86 architecture or machine is a 32-bit machine, and if I look at the addresses, each address, they're all the same size in hex. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is 32. Why did I get 8 times 4? Because each one of these is a 4-bit digit. Why are they 4-bit digits? Because it's hexadecimal. Next, the x64 machine is 64 bits. And if you count all the way through this, you will end up with, we'll count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You get 16 hex digits. 16 times 4 will be 64 bits. But notice something, the size of the integer in both of these machines is fixed. The language says 4 bytes, it's 4 bytes. Or the compiler says it's 4 bytes, it's 4 bytes. More correctly, some languages specify the size, other languages don't specify the size. That's up to the machine. Now here I turned around and run the program different times. Same program, I said, okay, 12 bytes altogether, 4 apiece. But this is the interesting part too. The starting addresses and ending address, well, starting address changes. But the ending address is always 12 away. The ending address is always 12 away. If you do the hexadecimal math, you'll find out there's the difference of 12. Sometimes it's really easy. This one here, 0 in C is 12. 0 in C is 12. Next, we're going to look at a loop. I know about addresses. So if you tell me the starting address of something, tell me where it ends, and tell me how they move from one address to the other, I can write a for loop. And I call this pointer fun. Here's my for loop, and here's what I'm going to do. I have my array, A, and I'm going to fill it with the number 1. And I'm going to do it the hard way with pointers. A is already a pointer, but I'm going to create another pointer, call it PA, for pointer to A. How do I know it's a pointer? I put a star there. What does it point to? It points to an integer. So what we're going to do is I'm going to, in my for loop, I'm going to have my starting point. I'm going to say, put the address of A inside PA. So now, in your mind, PA is really pointing up here. I'm going to erase the lines here. So PA at this point is pointing right to A. Next, I'm going to ask a question. Take a look at PA. What is it pointing to? Well, it's pointing to the beginning of A. Well, if it's not equal to A, the beginning of A, plus n integers later, this would be the end of A. If you could imagine, dot, 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 there's the ending somewhere over here. If it's not the ending, go into the body of the loop. Body loop says PA is an address. Go to where it's pointing and fill it with the number 1. So a number 1, a copy of the number 1, will be moved into the first position there. After it executes the body once, it'll go here and says add 1 to PA. But remember, when it's adding 1, it's actually doing this for you. Size of an integer. If we had doubles, it would be the size of a double. If we had an array full of mooses, it would be the size of a moose. Here's the code written in a more natural way. Here's my starting point. Here I'm looking for the end. Here I'm moving over. And this is the body of the loop. Notice I say it's the same idea as tell me the starting address of A, move over I. But when I say move over I mean the size of an integer. And then go inside. This does exactly the same thing. A few slides back, I said the minute you write this down, you will actually turn around and you have the compiler take A, that's the starting address, plus I times, I'm using a mouse to do this, size of, what is A filled with? Juicy ints. And so this will hop along, moving one integer at a time. Now I also use this range loop here. This only works because A, again I'm going to erase, excuse me, A is right up here. So the compiler knows where A lives and it knows the size of A. A is n. The compiler just looks up there and knows everything. So this will work here. Now we could get a little crazy. I call it coding madness. I turn around and they say, I'll start an integer I. I'll move my address of my array in here. I'll then ask, is the address in the array plus I, is this thing at the very end of the array? If not, I come in here, go to the address of A, move over I, and this says go inside and put the number 1. After that, I come back here, and this is simply I equals I plus 1. It's just 1, 0, 1, 2. This thing just goes 0, 1, 2, 3, because I is a fun-loving integer. It's nothing else. There it is, just an integer. However, when I get back here, it's still just an integer, but you don't see, but secretly, right here, there'll be times size of I, so that these two things are comparable. Of course, the right amount of sugar makes everything go down easier, and this is the much easier way to do it. I still don't like what I'm doing. I don't like what I'm doing here, but this makes life easier. Same code, getting cleaner. And here's the code even cleaner. because the array here is within the scope of this loop, that the array is defined in the scope, this range loop will work in both cases. What about functions? All right, here's a simple function. The idea is you give me an array full of yummy integers, tell me how big it is, and I will simply add 2 to all its elements. And they're full of integers. I set I equal to 0. I say, am I at the end of the list? Oh, please note, I have no safety built into this. I don't check if you gave me a null pointer or n is negative. I'm just going for it. Not the best way to program sometimes, often. I get to the loop here, and I have a z, but where the heck does z live? We don't have an address for z. We don't have a z. It says, when you give me an address, this is like a blank space. When you give me the address, I'm going to plop it in here. And what do I know about it? When I get the address of z, I will simply say plus I times, I'll say size, if I can spell it, size of int. The compiler knows all this already. Star plus equals 2. So it's not just an I. It says when I learn this address, I will do all this. Notice I still just test I to see if it reaches the count of elements. So here's my program that I'm going to use. There's its output, but I create an NA and an NB. This means the number of elements in A and the number of elements in B. I used uppercase to show that they're constants. So now I'm going to create A. There's A. I'm going to create B. There's B. I could have done it the previous way too. So now, add 2. I'm going to actually, the compiler will give the address of A here. And it'll give the number n here. Then A will extract each data item one at a time and print them out. Next, the address of B will go in here. The address of B, that's very important. We're not going to give it all these numbers. None of these numbers are given to it. It's just where does A and where does B live? And tell me how many numbers to go through. And you'll notice that the everything has 2 added to it right up there. So zooming in a little closer, we know what's going on. We're giving this thing an address, and there's an address being filled in here. And we know that there's a more complex expression, z, the address of z. Again, we don't know where it is, because z could be any integer array, plus I times, I'm just going to put parenthesis int instead of scribbling, int. Now, I'm not sure what's going on. I mean, I see my code, I'm getting the right output, but I want to go deeper. I want to find out what's going on in here. I want to find out where A and B live. So I'm going to add some code. Here's a line of code that I'm going to add to A. Add to, excuse me. When you give me a Z, I'm just going to print out its address. I don't really care about I know what's going on here. But I want to see the address. Next, well, I need to know what A and B are. So at the top of my code, right after A and B have an address, because in the beginning they don't have an address, they don't live anywhere yet until runtime. At runtime, they're assigned an address in memory. So I'll take a look at them. When I run the program, first thing I get are A and B. Right there, A and B. So I know A and B live. And I know I'm going to see the words address of Z. The first time I see it is when I use A. So I know this one is A. And I look. There I see 9 Delta Charlie, 9 Delta Charlie. This is A. So Z was using this address to move over and change data. And there we see it. Next, down here, we see the address 9 Charlie 4 appearing a second time. And both of these times are array B. So we see it's a passing it by address. And now we know why this is so powerful. This works. Add 2 will work with any array of integers. Just tell me how big it is, and this thing will work. And I don't need to do this anymore. In fact, it's just annoying to see numbers printed out that aren't needed in your code. If you want to look on syntactic sugar, here it is. If you like this thing, give it a thumbs up. It's encouraging if you give things thumbs up, that maybe it was useful. I thank you.